Hello everyone. We have just a few slides to discuss for chapter 6, as I mentioned in our last class. So instead of discussing these slides when we meet, I will just still provide it as a video. Okay. So last time we were talking about multiprocessor scheduling. Okay, and we learned that there are two different approaches to multiprocessor scheduling. One is using a common ready queue, so all the processors will share the same ready queue, and whenever a processor needs to schedule a task, a process you just pick one from the common ready queue. Okay, and the problem with this approach is that it requires synchronization across all the processors, and when we have many processors, many cores, that overhead becomes significant. Okay, so that is why the other approach is more commonly used by modern operating systems. In this approach, each processor has its own private ready queue, right? So generally speaking, they don't need to synchronize with one another, right? So, but the private ready queue-based approach brings a different problem, okay, which is we may have imbalanced work, okay, on the processors, okay. So the reason is that, right? So when we schedule processes to the processors, right? So imagine these are the processors, okay. So and these are their queues, right? So when we put processes into these processes private ready queues, we can only do that in the best effort manner, right? Because we can only do it based on our estimate of the amount of work that each process requires, right? So even though, so as much as we try to balance the work across all the ready queues, right? When those processes really run, some processes may finish up earlier than the others, right? As a result, we will have imbalanced load, okay? When the process is run, okay? We end up with the situation where one processor still has another work to do. Okay, one processor has a little bit of work to do, and one processor has a completely empty ready queue, right? So when the work becomes imbalanced, that becomes a problem, because when a process is idle, we are wasting the processor's resources. Okay, and so we need to do so-called load balancing. Okay, we need to balance the load across all the processors. Okay, so that we can fully utilize all the processors. Okay, and load balancing is only necessary for systems that use a per processor private ready queue, right? Because in the common ready queue or the global ready queue approach, as long as there's work to do, any processor can do it by running the process from by taking it from the common shared global ready queue. Now, to realize load balancing for the private ready queue based multiprocessor scheduling, there are two different methods. One is called push migration. What it means that we'll periodically I mean the operating system will periodically check the load of each processor and move processes from overloaded processors to the idle processors or less busy processors. Okay, so basically we examine the depth of each private ready queue, right? So if we see a queue with a lot of processes planning to run, and at the same time we have queues that do not have many processes or even empty, we will move processes from the busy process ready queue to the less busy process ready queue or the idle process ready queue. Okay, that's called push migration because the scheduler is pushing the work to a process ready queue. Okay. And another method is called a pull migration. Okay, what it means is that whenever a process becomes idle, okay, it will immediately pull a waiting process from a busy processor. Okay, so whenever a process becomes idle, it will check another processor's ready queue. If there's still work processes waiting to run, it will take one and run it. Okay, sometimes this is also called work stealing, because this process is stealing the work that is supposed to be run by another processor. Okay, it's called pull migration because looking from the perspective of the processor, it is pulling the work to the ready queue, right? So, but still, the migration is done by the operating system. Okay. So these two methods are complementary because push migration is more expensive because it involves multiple ready queues and requires synchronization across multiple reticules. So you have to do load balancing across multiple reticules. That also takes more sophisticated algorithm to do it. Pool migration is not expensive. Okay, you just take one process from one reticule. Okay, it's not expensive, but the problem is that whenever pool migration happens, that means we already have an idle processor, and while we are doing the migration, we are already wasting CPU cycles. Okay, so we want to avoid pool migration as much as possible, but we still need it just in case push migration does not work perfectly. Okay, because we cannot use push migration all the time, right? So before we get to do push migration again, it is still possible that a processor just finish up all its work and becomes idle. Okay, and again, because remember that the load balancing is done only in the best effort manner based on our estimate, right? And it is possible that before we get to do push migration again, a processor becomes idle, and when that happens, we must use pull migration immediately. Okay, so these two methods are complementary and are used together. In fact, in Linux, okay, so Linux runs the push migration load balancing algorithm every 200 milliseconds. If you still remember that the time quantum Linux uses about 10 milliseconds, right? So it means that every 10 time quantums, the Linux will use the push migration to balance the work across all the processors. And at the same time, Linux also uses a pull migration whenever a processor's run queue becomes empty. Okay. So now we talk about the load balancing. It is about migrating process across queues so that we can maximize the utilization of our processors and maximizing the overall performance of our system. Okay. Now, in contrast to load balancing, there's another technique called processor affinity. What it means that we will ping a specific process to a specific processor. Okay, and so it is the opposite from load balancing because we want to disable the migration for a process. Okay, why do we want to do that? Okay, the reason is that process migration involves overhead. Right? It takes time to move a process from one processor to another processor, and when a process goes to a new processor with a different set of caches, it also has to warm up those caches again, right? And during that period of time, it has to fetch its instruction data from memory, and we know that is a lot slower than getting them from a warm cache, right? So because of the overhead, for certain processes that are really performance critical, we do not want them to be migrated. Okay, and the processor affinity will allow us to do that. It will allow us to ping a specific process to a specific processor. Okay, so that so they always stay in that processor's reticule. Okay, and as a result, we minimize the potential performance impact to that particular process. Okay. So this obviously there's a trade-off here, right? So processor affinity will allow us to optimize the performance for specific processes, okay? But we may sacrifice the utilization of the processors because we cannot migrate those processes to balance the load, and as a result may sacrifice the overall throughput, overall performance of the whole system. And more specifically, there are two different affinity ways of implementing affinity. Soft affinity, in soft affinity operating system, we only try best to ping a process to a processor, but there's no guarantee. For example, if one processor becomes idle, it is still possible to move a process that is supposed to be pinged to a different processor to the idle processor. Okay. Now, in hard affinity, then the affinity is guaranteed, okay, no matter what, okay. And the operating system provides the system calls for applications to request affinity, okay. For example, set affinity is a system call that is available, I believe, on Linux, okay. Now, finally, let me conclude the discussion of this chapter with the scheduling in the real advanced operating system Linux. Okay, so in Linux, the scheduling is priority based. Okay, remember we talked about priority based scheduling before. Okay, and it supports preemptive scheduling. Okay, we also talked about that before. It means that the scheduler can force a process to leave the CPU even if it has not finished its CPU burst, okay, so that we can schedule another process. Okay. And specifically, Linux uses two priority ranges to differentiate two types of two classes of processes. Okay, so for real-time processes, they have a higher priority, so their priority values are lower. Okay, ranging from 0 to 99. And for time-sharing processes, they have a lower priority, and the priority values are between 100 and 140. Okay, and these priority values are also called nice values because in Linux we can use the nice command to assign the priority value of a process. Okay, and the priorities of real-time tasks, they are assigned statically. Okay, once they are set, they do not change. But for time-sharing tasks, their priority values are assigned dynamically, meaning that they may change when the process is actually run. Okay. Now this diagram illustrates how the priority values map to the two classes of processes we have in the system, right? So the priority value range from 0 to 140, the higher the lower priority, and the real-time tasks have higher priorities, and the time-sharing tasks have lower priorities. Okay, so finally, let me give you just a high-level overview of this advanced CPU scheduler that the user currently uses. It's called CFS, Complete File Scheduling. Okay, it's a relatively recent scheduler designed for multiprocessor scheduling in Linux. Okay, if you remember when we started have this movement into the multiprocessor, multi-core era, it's also recent, it's relatively recent. Okay, so the CFS scheduler is relatively new. Yeah. So in general, CFS assigns CPU time to each process based on proportionally to its less value. Okay, a lower less value indicates a higher priority, and which results in a larger portion of the CPU time. Okay, so if you remember how is the round-robin scheduler, right, which is a basic time-sharing scheduler, right? When we talk about round-robin scheduler, we talk about that each process we have the same time quantum, right, and then we schedule process one by one, right? So here we look at it. So in a real-world scheduler, CFS, right? It also does round-robin scheduler, but each process has a different time quantum, okay, which is determined proportionally to its priority. Okay, a higher priority process will have a larger time quantum. Okay, and more specifically, the priority of process is determined dynamically, adjusted dynamically based on this concept called a virtual runtime, called V runtime in short. Okay, so V runtime is the measurement of how long a process has run. Okay, so when we run processes, okay, so a process may not be able to use the time that we gave it to run, right? It may finish its CPU burst earlier than the time quantum, okay, the assigned time quantum. Okay, so we measure that, okay, using V runtime, okay, and a lower V runtime would allow us to increase the priority of the process. Okay, so a process that could not use its assigned time before, okay, will have a lower V runtime, and then the scheduler will increase the priority of such a process. Okay, conversely, a process that has a higher V runtime will have a lower priority. Okay, so now let's see how this dynamic adjusted priority is used to schedule processes in practice. Okay, so I just give you one specific example. Okay, the complete scheduler is a lot more sophisticated. Okay, if you're interested, you can read the code and learn it on your own. Okay, but in this simple example, we want to differentiate two types of processes: CPU-bound process and IO-bound process. Okay, so a CPU-bound process has a long CPU burst, can always use up its allocated CPU time, while an IO-bound process has a short CPU burst. Okay, it just does a little bit of CPU and then it will be blocked for I/O. Okay, so what we want to do is that we want to prioritize this I/O-bound process whenever it is ready to be scheduled. Okay, so the reason is that because I/O-bound process does not use a lot of CPU, right? So for fairness, when it is ready to run, we should schedule it. And also for the sake of interactivity, right, when the I/O that this process is waiting for is ready, we should allow it to immediately process the IO. Okay. So because of this reason, we want to prioritize the IO bound process when it is ready to run, okay, over a CPU bound process. Okay. So now let's see how this is realized in CFS. Okay. So let's assume initially these two processes, they have the same NAS value. Okay. So they are allocated the same amount of CPU time, right? So they have the same CPU quantum. Okay. And the CPU bound process will always exhaust its time slice because it has long CPU burst. Okay, so as a result, its a read runtime equals to its time quantum. Okay, and in comparison, the IO bound process will not be able to use its time slice, and it will have a shorter read runtime than the CPU bound process, right? And we just learned that a shorter read runtime would actually boost the process's priority, right? So eventually, the L-bound process will have a higher priority than the CPU-bound process, right? As a result, whenever the L-bound process is ready to run, it will be able to preempt the CPU-bound process, okay, so that we can process the I/O immediately. Okay? So now you see how this is, how everything works out, right? When we in this read runtime based scheme of adjusting priority dynamically and also adjusting the scheduling dynamically. Okay. So this concludes chapter 6, and here are the problems that I strongly recommend you to work on. Okay, to make sure you really understand the materials. Okay, and be prepared for the midterm.